morning everyone. Here in the electromagnetic theory, now we are going to see about Maxwell's equation, where the Maxwell has given four equations. First equation you can have it from Ampere's law. So according to the Ampere's law, closed interval of H dot dl equal to I. Closed interval of H dot dl equal to I, where H is the magnetic field intensity and I is the current enclosed. So closed interval of H dot dl. Current can be represented as current density into area. So surface interval of Jc plus Jd into ds. Where Jc is called conduction current density, Jd is called displacement current density. So closed interval of H dot dl. This can be written as sigma e, where Jc can be represented as sigma e plus epsilon dou e by dou t, where Jd can be expressed in terms of electric field intensity as epsilon e dou e by dou t. So this you can have it as Maxwell's equation in integral form. Maxwell's equation one in integral form. This can also be applied to, can have it in the differential form. This is what we call it as integral form. We can convert them into differential form to either Stokes theorem or divergence theorem. So through Stokes theorem, first we are going to convert them into a purable form, then with that we can compare it. So we can see that one. So closed interval of H dot dl by Stokes theorem. By Stokes theorem. Closed interval of H dot dl can be represented as surface interval of del cross H into ds. Now we take this one as equation number 2. So compare 1 and 2. Compare the equations 1 and 2. Compare the equations 1 and 2. So surface interval of del cross H into ds equal to surface interval of sigma e plus epsilon dou e by dou t into ds. So this can be expressed as del cross H is equal to sigma e plus epsilon dou e by dou t. So this equation is called as Maxwell's equation in differential or point form. Maxwell's equation in differential or point form. So next one from Faraday's law. From Faraday's law. Next one from Faraday's law we can derive Maxwell's equation, where we have with the potential and magnetic field. This can be expressed as minus dou b by dou t into ds. Once again the potential and the electric field can be expressed as V equal to E dot dl. This you can have it as 4 and this you can have it as 5. From 4 and 5. From 4 and 5. You can have closed interval of E dot dl equal to minus double interval of dou b by dou t into ds. So this you can have it as equation 6. Equation 6 is called equation 6 is called Maxwell's equation 2 in integral form. Once again I am applying Stokes theorem. So closed interval of E dot dl that can be written as del cross E into ds. This is equation number 7. Now you compare 6 and 7. Compare 6 and 7. So del cross E into ds is equal to minus dou b by dou t into ds. So from that what you can obtain? Del cross E equal to minus dou b by dou t. So this we can represent this equation 8, where equation 8 is called Maxwell's equation 2 in differential or point form. Next we can go for Maxwell equation 3. Maxwell equation 3. This is from Gauss law. So all of you will know about the Gauss law. So from Gauss law we know that D equal to double integral of Q equal to double integral of D dot ds. Flux density of closed path equal to the charge enclosed. Once again, charge can also be represented in volume charge density as Q equal to triple integral of rho v into d. Now comparing these two, we can have it as 9 and this we can have it as 10. Comparing 9 and 10, we can have it as volume integral of rho v into d is equal to surface integral of d into ds. Take it as equation number 11. 11 is called Maxwell's equation 3 in integral form. So for the first two theorems, we have applied Stokes' theorem to convert integral to differential form. Whereas here we apply divergence theorem. We apply divergence theorem to convert integral form to differential form. Apply divergence theorem. So when you apply divergence theorem, the integral of d dot ds is equal to volume integral of del dot d into d. So we have 12. Compare 11 and 12. Compare 11 and 12. Compare 11 and 12. So what you get as del dot d equal to rho v. Del dot d equal to rho. This is called Maxwell's equation 3 in differential or point form. So finally the fourth one. Very simple one. It is from magnetic Gauss. From magnetic Gauss. So according to magnetic Gauss law, surface integral of B dot ds equal to 0. Magnetic flux density around the closed path equal to